Okay, we are recording. So let me hand the floor over to this Pipette Group. You can share your design with us.
All right. Maybe.
Hello, we are Spencer. We are a team of 5 mechanical engineers. I'm going to let everyone introduce themselves.
All right. Hi, I'm Cindy.
I'm Garrett.
I'm Nicola.
Hi, I'm Solomon.
And I'm Zachariah. And now, before we get on to the main story, we got to talk about the prequels. You see, last semester, we all took a class called Mechanical Design 2, where we were tasked with designing an autonomous micro bioreactor. Our customers then and now were the UF Biofoundry team. We were given a plethora of complex customer requirements. We had to break the system down into 6 subsystems, one of which was this liquid handling subsystem shown here, also along with the gantry system. And now we are in Mechanical Design 3, where we have a new hope. We must focus on just one subsystem, the liquid handling, where we have to design an autonomous pipette. We have 28 customer requirements with 5 ones that I just want to highlight real quick. One, the range, 100 microliters to 1,000 microliters. Another, that the error must be less than 5 microliters. For reference, the average human teardrop is 6 microliters. Our budget is $100, and we absolutely have to avoid aerosols and cross-contamination. And of course, the mechanism must have a lifetime of 10 years.
All right, before we get into the juicy details of our project, here's an overall view of our final design. So starting on the far right side, we have the NEMA 17 motor with a lead screw. And this also came with a lead screw nut, which is that brass piece seen a little bit further on to the left. We made this nut housing attachment, which is a special piece as it has these 2 protrusions sticking out of the sides of it. These interact with the slots in the housing, which is the main piece in the center of the image. And we'll touch on the details later, but that's one of the key components of our assembly. Another main subsystem is the piston and the control volume, both of which are made of 6061 aluminum and precision machined. These 2 work together to create a seal using these O-rings, and that allows us to draw and dispense liquid as we choose. The last subsystem is seen on the far left with the tip ejector, which is also made of PETG, just like the nut housing attachment. This serves the purpose of ejecting the tip, and it's attached to the piston, so it moves with the lead screw as well. It's attached using these knurled screws. So that's an overview. Now we'll go into some more details.
Great. Thank you, Sala. So one of the very first issues that we wanted to tackle was obviously how to withdraw and dispense the liquid in our pipette, which we decided to go with that double O-ring piston design that you saw previously. So one of the main things of this design is that we need to translate the rotational motion of our motor into linear motion. And that leads us to 2 of our major design decisions. One of which is that nut housing attachment that Salo also mentioned. Which you can see in the bottom, which is the inner housing slots that you can also see in the cross-section. That housing attachment is attached to that lead screw nut that we mentioned earlier. It then is allowed to slide. Can you guys hear me now?
Yeah, so Cindy, try killing your video to see if it helps fix the audio problem. Okay,
cool. Can people hear me now? Is it clear? All right, great. Can I ask where you guys lost me?
Right from the beginning.
Okay, right in the beginning. Okay, I'll just start over then. Right, so one of the very first issues that we obviously wanted to tackle was how to withdraw and dispense the liquid with our pipette. And so one of the So we did this with that double O-ring piston design. And with that design, we needed to figure out how to translate the motor's rotational motion into linear motion. And that leads us into two of our major design decisions, one of which is the nut housing attachment that you see in the bottom right corner. And so with this attachment, it screws into the lead screw nut that you saw earlier. And it has those two circular flanges, which is the inner housing slots that you can see in the cross-sectional picture in the upper right-hand corner. So when the lead screw nut goes up and down, so does the nut housing attachment, which is aligned with the inner housing slots. And that allows us to have smooth linear motion that we need for our pipette.
And so we figured out how to get the linear motion. What we had to tackle next was how do we avoid cross-contamination? We got to dispose that disposable tip. And so this was the original kind of final design that we were going to go with. We had our solenoid actuator on the outside of the housing, and it connected and wrapped around where the disposable tip would be pushed into with this tip ejector attachment device thing. And spoiler, we really didn't like it. It just added so much complication. We had extra cost with the solenoid. We had tight tolerances and an extra bending moment with the tip ejector attachment. It was just a flimsy design, and we really didn't want to use it. So we racked our brains and we figured out we could do this. The slot strikes back. So we remembered only the controlled volume, the vacuum, needs to have that perfect seal. That means we could do a quick calculation based on the diameter and the height, and then add some extra height for the max volume that we're going to have to be withdrawing. And that way no back drawing occurs when we have the water being withdrawn into the mechanism and going past the disposable tip. So all that extra space we have, we can have the slots extrude out of the housing, and then we can have this exoskeleton shell-like tip ejector wrap around the entire thing and connect to the plunger and have it move with it. That way we have a cheaper design. It's simpler with everything being in one axis. And I have some pictures here to show you guys what it ended up looking like. So here's like a see-through version of where you can see the plunger being attached to the shell-like tip ejector. And then here's just the tip ejector by itself. Bam. And so just like any engineering project, we had our attack of iterations. After iterating and iterating and iterating, figuring out little things and moving forward, we finally reached our final design.
So here we have the rise of the pipette. This is the completed model that you guys saw an overview of earlier. This completes all the required customer demands that were given to us at the start of the project. And I'll just run you guys through some of the stats. So the piston and the CV are both made of 6061 aluminum, while the housing, the tip ejector, and the nut housing attachment are all made of PETG, and they're made using additive manufacturing. Now, something that's important to note is all the fasteners that were used on our project are M3. So most of them you require Allen key to use, but some, such as the ones that attach the tip ejector to the piston, are just knurled, so you can even do that manually with your hands. So we try to make it as easy for the customer as possible to take this thing apart and put it together. So here we took a couple timed runs of how long it took us to put it together and take it apart. And we have the times here. So if someone wanted to run some experiments back to back, they could just put it together and take it apart in under 10 minutes. Another feature that I think makes it easier for customers to use is the control volume attaches to the housing using a threaded, so it's basically threaded, and the housing has female threads where you can just hand tighten it and you don't need any tools for that. So it makes it easy if you need to get in there to clean whatever liquid you're using in your last experiment.
Looking a little bit more at some of the physical specs of our device, the total weight is 458 grams, which falls well below the customer requirement of 5 kilograms. The dispensing rate is 910 microliters per second, And that does fall just below of the maximum dispensing rate of 1,000 microliters per second. And we do consistently get error below 5 microliters as well. And here's just a little animation of it drawing and dispensing and then ejecting the tip. So another customer requirement was that there would be no aerosol creation. So to ensure this, we did a quick Reynolds number analysis. So looking at a Reynolds number of 4,000, which is the highest we can have to maintain laminar flow and avoid aerosol creation, we obtained a maximum velocity that we can dispense at without creating these aerosols of 3.92 meters per second. Looking at the desired volumetric flow rate of 1,000 microliters per second, we found that we can actually dispense about 2.5 times that before we have any issue with aerosol creation. So there'll be none of that from the dispenser. And then we also so we recognize that a lot of these calculations are being done with the properties of water, but it's not fair to assume that our customers are just going to be using water at all times. So we wanted to create some sort of metric to see what fluid compatibility they might have. And so looking at this flow rate again, of 1,000 microliters a second, we figured out a ratio of the dynamic viscosity and the density of the fluid that would be able to still reach this target of 1,000 microliters a second. And this number 2.86 times 10 to the negative 6 is a value that we can obtain we'll get values well below this for most water soluble things. It isn't until we start testing more dense things like oil that we have problems.
One of our main concern was the bending moment generated on one of the most critical part of our assembly, which is the knot housing attachment, as you can see on the top right picture. We assume that the knot housing attachment will move down and hit the end of the slots of our housing, and therefore generate a bending moment in the middle of the cross section of the attachment. And therefore, we have designed the thickness and geometry of such part by analyzing the force generated by the lead screw, which was obtained using the lifting torque, which was known to be 0.4 Newton meters and mean diameter of 8 millimeters and lead of 8 millimeters. And using the equation shown below, we have assumed that the coefficient of friction for contact between steel with some oil and brass was 0.1, and therefore the force generated by the lead screw was 472.65 newtons. And as you can see, we have assumed that the attachment was just a beam supported by 2 pins, and it is symmetric. Therefore, the reaction forces will be just half of the force. And as we can see next, we have determined the maximum tensile stress on the most critical cross-sectional area of the attachment. Since it is symmetric, the shear will be maximum at the middle, and therefore the sigma max was 45.4 megapascals, which is a little less than the yield stress of the PETG with 95% in fill, which resulted to be 58.6 megapascals. Furthermore, we have printed the attachment with layers perpendicular to the axis of the movement, so that the layers of the filament will not go under pure shear, but they will go under a smaller compression and tension stresses.
And so moving on to another failure point we wanted to analyze, we definitely wanted to take a look at the O-rings, since they're facing constant frictional force from the pipette moving up and down with withdrawing and dispensing the liquid. So to do that, we created the force body diagram that you see on the right there, where F sub M is the force applied by the motor that we just saw in the last analysis. F sub W is the weight of the piston, F sub F is the frictional force, and F sub IP is the force caused by the internal pressure from our controlled volume. And so putting all of these into a net force equation, we figure out that frictional force is about 462 newtons. And so this is a useful force to be able to figure out, because then we can figure out the bending stress that it causes on the O-ring. And from there, that is also useful because we can assume that due to the motion of the piston, this bending stress is a perfectly reversible cyclic load. And so with that, we can then figure out the life expectancy of the O-ring. And so we take that bending stress value along with factors such as the fatigue strength factor, the ultimate strength of the O-ring material, as well as its modified endurance limit. And from there, we can figure out how many cycles this O-ring will last. And so that ended up being 9.58 times 10 to the 52nd power, where infinite life is considered anything above 10 to the 6th power. So O-rings are confirmed to achieve infinite life, which definitely exceeds the 10-year customer requirement.
Okay, here we have the third part of the force analysis Awakens. This is the cost benefit. So on the table on the left here, we have a cost table of our current model. So here we have like a bill of materials of all the things we use. We have the 6061 aluminum for the control volume and the piston. This comes out to just under $4. We have the PET G for the tip ejector, the key nut attachment, and the housing. This comes out to $4.30. The NEMA 17 stepper motor is just under $30. We spent about 78 cents on fasteners and O-rings. And for the magnet assembly that connects the pipette to the rest of the bioreactor, costs about $19. So that brings our total cost per unit to $56.78. Now, we were just wondering if we made all those PET G parts out of the same aluminum that we used for the control volume, how much would it cost? So we ran a little analysis, and based on like the stock that we needed with extra stock for machining and all that, it would come out to $76.43 alone. I mean, yeah, alone just for the stock. So when you compare that to the $4.30 that we used for those parts when we were using PET G, that's saving $72.13 per dispenser. So it's pretty, it'll give you a lot of savings over the course if you're mass manufacturing these parts.
And so now we have the revenge of the undergrad, where we just have to prove it works. And in order to do so, we have our own testing methodology. First, we have the environmental conditions. This means that the testing area has to be draft-free and have a temperature range of between 15 degrees and 30 degrees. Next, we have to prepare for testing. So we make sure to leave all the equipment and the mechanisms, the pipette, everything that we would be using in the room for 2 hours before we begin the testing. That way everything reaches ambient temperature. Next is the leak test. Here we set everything up and we withdraw a number of different volumes and watch the disposable tip and make sure that there is no leakage. We watch for 30 seconds at least, and thankfully there were no leakage. Then there is the gravimetric measurements. Here we withdrew and dispensed a number of different volumes a number of times, and we dispensed it onto an extremely sensitive scale. And then finally, we have the data analysis, where we have all that data that we did on the gravimetric measurement, and we analyze it. And how we did so is on the right side with the mean volume calculation shown, and then how we plug that in to get accuracy and precision. In the bottom left table, we showed that we did tests. I wanted to show the test we did for 100, the minimum microliters, 500 in the median range, and then 1,000 microliters. And as you can see, we calculated accuracy, repeatability, standard deviation, and the coefficient of variation. Thankfully, everything was within the customer requirements.
Okay, so going more into detail about those gravimetric measurements, we use that process in order to create the calibration curve that you see on the slide now, in order for us to hit any volume within our given range within our given error. So the way we did this gravimetric analysis was we inputted certain step values into our pipette code, And then we measured how much liquid our pipette could actually withdraw with that step value. And so before we even did this process, we already had an initial estimate equation based off of our motor step size and our control volumes in a diameter. So with those two values, we could figure out how much volume one step of our motor could actually achieve. And so we used that equation to figure out then how many steps it would take for us to withdraw and dispense 100 microliters. And we also calculated that value for every volume in increments of 100 up to our maximum volume of 1,000. So 100, 200, 300, and so on. So once we had all of those step values, we inputted those into our code and measured how many microliters were actually withdrawn with those step values. And then we did that for each step value we had 3 times. And so with those step numbers, as well as the measured volumes that we had, we plotted those in the graph that you see and fit a simple linear equation to it, of which the numbers you can see on the left side. And that's the equation we ended up putting in our code in order to hit any volume we need within the 100 to 1,000 microliter range.
Okay, so we now are showing you a quick video of our working prototype. We've just dispensed 1,000 microliters, sorry, into that red cup, which we will then be measuring on the scale. You can see our tip eject a second ago as well. Keep in mind that 1 milligram is the same as 1 microliter. So right now we are at 1,001 microliters, and we end up reaching an equilibrium on the scale at 1,000.7. So well below that assigned tolerance. We'd like to take a moment to thank the entire MAE teaching team for all the help they gave us on this project, as well as our sponsors at Northrop Grumman and Cummins. Thank you so much for attending our presentation, and we are happy to open the floor to some questions now.
Hey guys, this is Tom Singer from Northrop Grumman. I want to start off by saying good job. I appreciated your theme. I do want to know who Spencer is and why you're dissing him.
I had the same question.
Mm-hmm.
Well, let's ask Nico.
Well, it took us a minute to like came up with the name, and we just wanted to like be a little funny. So I thought that some wordplay was gonna do the work for our project name, and I just thought about dispensing, and then this Spencer.
Well, he sounds like
Whatever
a jerk,
Spencer
so.
You don't like.
Yeah. Okay. So a couple of questions. I'm going to work backwards, I guess. You'd mentioned that you're saving like $70 or so by making things out of with 3D printing as opposed to out of aluminum. But 3D printing doesn't scale very well, right? So if you're looking at producing a significant number of these, you're probably looking, if you're staying with plastic parts, you're probably looking at something like injection molding. Does that have any impact on your design? Design for 3D print versus design for injection mold?
I'm sure it would have some impact, but we kind of just realized that, that was something that was probably going to need to happen if this was scaled up on the production line, but we haven't actually looked that closely at what design elements would need to change. That being said, plastic injection molding does work well for some of these more complex parts, and we don't have anything that's like all that complicated, so I think we'd be okay.
I also think SLS 3D printing would be fine as well. Like with a Formlabs 3D printer, you can fit a whole bunch of different prints in a clustered print, and it would be not too terrible in manufacturing at a larger scale.
Okay. I appreciate the concentric design of the pump. And I know one of the groups that we saw yesterday was talking about having it offset, having that lead screw offset caused racking, and they had to redesign, and they ended up concentric. And so I can appreciate that design from a like a structural efficiency point of view. The anti-rotation device. So speaking of structures, right? I'm a structures guy. The anti-rotation device. You said you did essentially a beam analysis on this guy, right? Yeah, there he is. And you're saying that I guess the critical section there is right at the root of the little tab coming out. Is that correct?
Yes.
Okay. I guess it kind of depends on the relative dimensions. I would expect the from just a far field stress perspective, the critical section might be at the center rather than at the edge. That your moment might be higher there, and your moment definitely is higher there, and your cross section might be not enough bigger that you wind up finding that's critical. But right at that corner, right? So you're showing a part with sharp corners right here, right?
I'm sorry. What type of corners?
Like sharp, like sharp corners, right? There's no fillet, there's no radius at that internal corner, right? So as you bend that ear, right, that ear, the bottom side of it is going to go into tension, and tension and sharp corners are a bad combination, right? Now maybe that's not such a big deal, but when you're saying that your load case is something like 80 or 90% of your strength allowable, that starts to become a concern. And I gather that this is like a stall load condition, so it's something that you have to have some other failure in your system to hit. So maybe you're not hitting this repeatedly. But I'd be concerned with, from a strength perspective, if you've got a stress concentration, and then certainly with a fatigue perspective, if you have a stress concentration there. And the other thing I'd point out there is I think you were using it sounded like room temperature material property. And my understanding is this is going in a chamber that is as much as 70 degrees Celsius. And so I would be concerned with like heat effects if you're losing strength with temperature, and potentially even losing strength with absorbed moisture. I'm not sure. Not every plastic is going to have that issue, but certainly some of them do. And then you've also got to consider, again, if you're sticking with a 3D printed part, the strength of the part itself is not necessarily going to be the strength of the bulk material, so you're going to lose some to that as well.
Yes, I just wanted to mention that this analysis was performed for some particular cases, since we have assumed that in the eventuality that the not housing attachment was going to be pushed down by the motor with extra displacement, the power supply was going to draw much more current, and ideally you would set the ampere of the power supply such that it will stop the motor from working once it hits the one specific threshold. And
this is kind of like a failure condition, and maybe you can be a little more lenient on how strong it needs to be. But if you're going to do the analysis, I think certainly pay attention to things like stress concentrations and material property degradation.
Yeah. I also wanted to point out that ideally the material was going to be done in ABS plastic, just to reduce outgassing of the part itself, and so it will not be conditioned as much from moisture.
I've got a few more, but I'll see if anybody else wants to take a shot.
Yeah. Any other panelists want to jump in with a question?
All right, Tom, throw them at us.
All right. So I think you had mentioned when you're talking about the splashing or whatever the term we're using for the liquid dispensing, aerosolizing, that you were looking at keeping things under a Reynolds number of 4,000. Other groups I've seen have been using 2,400. Not being a fluids guy, I couldn't tell you which one is more appropriate, but certainly this is the first group I've seen, at least, that's using a threshold this high for laminar flow.
Okay, that is definitely something we'll need to double check then. It's possible that we skipped the transitional flow bit and went straight to the threshold for turbulent, because transitional flow would still create some aerosol. So we'll need to double check that. But hopefully, given the fact that we're still safe by such a large factor.
Yeah, I think you've got room to lower that down to something maybe more in line.
Yeah.
So I'm not too concerned about the impact on your design. What about dead space in your system? Because you've got to give yourself room, I think, to like over dispense to pop. This is exactly the animation I wanted to see. You've got to give yourself room to like drive your lead screw down far enough to eject the pipette, right? So that's taking up volume that would otherwise be like usable volume in your system, right?
Yeah, and so we added extra height. That way we could, so like theoretically we could do more than 1,000 microliters, but obviously we don't choose to, because then it would run into the disposable tip.
Right. So is there any problem with having that dead space if you need to potentially like flush out your chamber that you're not able to dispense 100% of the fluid?
Thankfully, there were no problems. Honestly, it seemed like just full of solutions like plus, 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 pro, pro, pro. And after multiple tests, we would always check if there was any left in the disposable tip, and there never were. The pressure of the vacuum worked.
We did some calculations to make sure that the dead space was appropriate too. And we figured out how much space we actually needed and then how much space the screw took up and then adjusted accordingly.
Okay. Yeah, I guess it's kind of more of an operations question, right? So as this is, doing its thing within a microbioreactor, if they decide, hey, we need to, flush something without changing a tip, if that's going to cause a problem because you've got, some fraction of your container is essentially like fluid space that you might want to flush out. So, and again, even changing your tip, right? If you change the tip, you're pushing all the way down. It looks from the animation like that's at least pushing out all the fluids. Maybe that's sort of the saving grace here. But yeah, it's something that I'd wonder from a overall microbioreactor system standpoint.
I'd like to say. Oh, sorry.
I was just going to say, we originally had the lead screw and the housing a little bit longer. So originally, maybe it would be possible to draw more liquid than we needed just to flush out that inner control volume. But we decided to pursue a shorter design just because we're trying to like save as much space as possible. But it's worth considering that there's advantages to having a longer design as well, as you pointed out.
And then the one other thing I wanted to ask about, when you were looking at the O-ring analysis, you said that you calculated a friction force on the O-rings?
Yes.
And that was I think on the order like 460 newtons?
Yes.
Which is on the order of 100 pounds? Is that, I mean, I don't think in metric very often, but 100 pounds seems like a lot to push a plunger.
Yeah, so we were, this is sort of a, you could say like worst case scenario, which is why we used the value that Nico had calculated for the torque from the motor. So I took that since that seemed to be the maximum force the motor would produce onto the O-ring. If that answers your question, which is why it's quite a high number.
Yeah, that's a real high number.
Yeah, I should have mentioned earlier that this is a sort of worst case scenario. All forces included at their maximum type analysis.
Okay.
Yeah.
I'll keep going until you stop me.
Sadly, we've reached that point, Tom. So
okay.
Sorry. Yeah, we're actually 6 minutes over. So as usual, when Tom is in charge, things go over time. So I'm working on getting better at that.
Only 6 minutes, not 60. This is progress.
Little steps, small
It is
victory.
progress. Well, I get excited about it, especially when it's like thermal fluid stuff. Like,
I had to stop myself from chiming in on all of the fluid aerosolization stuff because I'm not sure just looking at Reynolds number is the right way to do it.
Oh,
But
it's a
that is a completely separate discussion.
okay.
yeah. I think it's a necessary but not sufficient condition to avoid.
It's a Rayleigh-Taylor instability of a jet stream of fluids of different viscosities traveling relative to one another that causes vortex shedding and droplet formation. It's a weird phenomenon, but the first step is turbulence, but you can get it to form droplets even if it is laminar.
Okay.
Okay.
Know that.
So
Thank you.
Okay. So on that note, we'll wrap it up there. Thank these guys for their creative approach to presentation with I think there was a Star Wars theme, right? Like,
Yes, it was
okay,
all Star Wars.
good. I was
Maybe.
like,
I would
Maybe.
hope.
yeah, even I recognize that. So, yeah, we appreciate that. That woke me up a little bit because we've been, this is what the 8th or 9th one of these. And so I'm like, oh, okay, that's cool. So we appreciate that creativity and all the work that you guys have put in this semester to bring this design to reality. And we'll wrap it up there. Thank you.
Thank you.
Thank you guys.
Thank you guys.
Thank you.
thanks, guys.
Good job, guys.
We really appreciate all the feedback.
Yeah. Spencer is actually one of the stormtroopers.
I knew it. There was some connection. That's awesome.
All right. Have a good one, everyone.
Have a good day.
All right. Have a good break, everyone.
Thank you
Bye.
guys.